Welcome to the practice video for topic 1. In the last video I showed you how to find the area between two curves. In particular, we saw that sometimes that would require splitting the area into two sections, and sometimes it was possible to use the variable of integration dy instead of the dx that we're normally used to. If you are still confused about those last few questions, about choosing which variable of integration is better and setting up the Riemann sum, I'm going to recommend that you stop before going on to the practice problems. And I actually recorded a second version of the first lecture in which I go into a lot more detail. Of course, it's longer because I spend more time talking about these practice problems, but if you are still confused about when do I use dy, when do I use dx, as soon as I'm done talking, on the side of the screen, you're going to see a YouTube link pop up. If you just click that YouTube link, you can skip through it, maybe just watch a couple examples, but make sure that you truly understand this foundational concept before going on to trying the entire problems. That's what comes next. Great, so I'm going to assume that you are comfortable choosing which variable of integration is to use. In this video, you're basically going to go through 15 practice problems, and I'll let you just do it on your own pace. Before I let you do that, I want to cover a few common misconceptions about how you set up your integral. In particular, you can see the 5 tips on the screen. I'm actually going to give you some pictures to go with those tips. So at this point, you're probably comfortable with the idea that in order to estimate the area between two curves or of a specific region in the plane, you're going to want to use a rectangular approximation, and you'll visualize filling that area with rectangles, and then use that rectangular approximation to help you come up with an integral. The problem is if you're not careful, your visualization of those rectangles might actually make no sense. Look at the 3 pictures on the screen. Can you tell what's wrong here? Out there are actually a ton of problems with each of these graphs. The easiest one to explain is probably this one on the end right here. The problem there is clearly that the rectangles don't cover the whole area. So if your Riemann sum represents these rectangles and kind of the limit of these rectangles as they get infinitely thin, your Riemann sum and your integral aren't going to represent the whole area that you want. Even if you write the integral correctly, you're going to be missing something. Okay, that's a pretty easy one to avoid. Totally self-explanatory. Let's talk about this middle one here. The problem with this side, the heights of each of these rectangles are determined by 2 points that are part of the same function. Why is that a problem? Well, the best way to understand why it's a problem is think about the next step. The next step here would be to write the integral. Now, since my rectangles are vertically oriented, this is going to be an integral with respect to dx. The little widths of the rectangles are dx's. And so what do you have to multiply times dx? You have to multiply the height. And normally we calculate the height by subtracting 2 values, the value of the y at the top and the value of the y at the bottom. The problem here is that both of those y values are part of the same function. Suppose we call this function f of x. We would be finding f of x minus f of x, but that's actually going to turn out to be 0 because it's the same function. So when you draw your rectangles, each rectangle should always have 1 point on one function and 1 point on a different function, or at least on the x-axis. These rectangles are fine because they stretch from the linear function to the parabola. So those rectangles will work out fine because these will be like an f and a g. But you can't have rectangles that stretch and touch 2 points on the same function. The same is actually true for these horizontally defined ones. For the horizontal rectangles, this means we're integrating with respect to dy because the thin part of the rectangle is a little snippet of y. So we'd be multiplying the length times dy. But in this case, at the top here, these rectangles, their length is determined by 2 points on the same function, which means maybe we're subtracting x1 minus itself. And that's going to cause confusion. It's not going to work out. Okay, and then there's actually yet another problem with this last one, in addition to the fact that these rectangles are poorly defined, as were those over there. The last problem right here is you can't have 2 rectangles that are kind of like stacked up this way. And again, if you're integrating with respect to y, stacked up will mean that they're occupying the same little interval of y. If we were drawing vertically oriented rectangles, we would not be allowed to have a rectangle like this and then another rectangle like that. And the reason for that is, if you think about it, your integral, your Riemann sum, is only designed to move in order one by one. So like this rectangle, or this series of rectangles, we could go first, second, third, fourth, fifth, and get through all of them. Whereas here, we would cause confusion. If we tried to start here and go 1, 2, 3, 4, 5, and count all the way up to the top, we would never know when to count those rectangles. They would actually get missed by your integral. Okay, so 3 things to watch out for. Make sure your rectangles cover all the area, make sure your rectangles don't have 2 edges on the same function, and that all of your rectangles are designed to go from one function to the other in the same way. And then finally, when you draw your rectangles, you should never have overlapping rectangles in order to try and fill the area. So how do you actually avoid these mistakes in practice? The trick is all about making the right choice for your integral of your variable of integration. In particular, if you take a look at this first one, imagine if instead of drawing horizontal rectangles here, I drew vertical rectangles. They would go from here and then here and then here. Do you see how we would eliminate the problem? Each of these rectangles would go from one function to the other. They would all stack up in an even order, and we would have nothing overlapping. Similarly, if over here, instead of doing dx, which is what I currently have, if I switched to using dy and drew my rectangles horizontally, I would go from the bottom, and each of these rectangles would go from one function to the other. It would be a smooth, continuous list, and we would cover the whole area. In practice, you're not always going to know right away. So to make sure you have the right choice and are avoiding these problems, it's all about the thinking process. So one of the reasons I don't like to overemphasize using steps is because sometimes students use steps as an excuse to not think. And which is why I've sort of given you steps here, but I want to really emphasize this right here. I've seen so many students go straight from the sketch to writing the integral, and then solving the integral and getting an answer which is the correct answer to the integral, without realizing that the integral they wrote doesn't actually describe the area they want to find. And the key to not making that mistake is to stop and explicitly think about what you're writing, both before and after you write the integral. I'm going to model doing this the wrong way, so you can see how easy it is to make a mistake. So let's suppose I'm new to finding the area between 2 curves, but I get this idea that we're supposed to write an integral. The area is going to equal a definite integral, and the definite integral is going to go, well, it looks like this shape starts at maybe 1, so I'm going to say it goes from 1, and it looks like it ends at 6, so from 1 to 6. And then it looks like the top function is the f of x function, which normally we would have an actual expression for, but we'll just say f of x for now. So I'm going to take f of x and subtract what appears to be the bottom function, which looks like g of x is kind of underneath. And then, of course, I end with dx, and that's just because dx represents the widths of each rectangle. This is a perfectly good integral, and if I had equations for f and g, I could very easily solve it. But this integral has nothing to do with the shape right here. Uh-oh. Okay, so where did we go wrong? Well, let's suppose I did write that integral, and maybe that really is your best first instinct, and that's fine. After you write the integral, let's think about what this integral is really saying. This integral is saying, okay, start at 1, here I am at 1, and draw a little rectangle that has a width that's a small section of x, and whose height goes from f of x on top to g of x on the bottom, and those are both y values. So I could draw something like that. This seems fine so far. And so then the integral is telling me keep going all the way till you get to 6. So there would be another rectangle here, and here, and here, and each of these rectangles should go from f of x on top to g of x on the bottom, which all looks fine until right here. And here, my actual area is going to differ from the area that the integral is saying. So I'm going to draw what the integral says. The integral says right here, wherever I am, to go from wherever f of x is down to wherever g of x is. And so I would draw this rectangle. This is the rectangle that my integral is going to calculate. But is this the rectangle that I want? No. In fact, the rectangle that I would want is this one. But I can't use an integral with an x variable of integration to find this one, because this is one of our mistakes that we warned you about. The mistake of having 2 points that are part of the same curve. So I've learned two things. I've learned that this is the wrong integral, and I've learned actually that I should not be orienting my rectangles vertically. If we try horizontally, and maybe you can't see that it's going to work before you try it, try sketching it horizontally. What it would look like. And as you can see, this is much more promising. Each of my rectangles have one end on each curve, and my rectangles are one continuous section. They don't like overlap in any way, and they do cover all of the area. So we still have to write the integral. This time I'm going to model the correct way to think about it. Who are more verbal learners, this is exactly what you want to think. After you've got your sketch, you need to think to yourself, if I start at some particular number and keep drawing rectangles with this particular base and this particular length all the way until I get to some other number, then my rectangles will fill the whole area. We've got a picture that says this. We just have to interpret what the picture is saying. Basically, we're looking for 4 different things: a starting number, an ending number, an expression for a base, and a length, or sometimes you think of this as a height. So here's how I translate that into my actual integral. My rectangles are oriented horizontally. Their base is this small segment of y, which means the base expression is going to be dy. Since my variable of integration is y, the starting and ending numbers also have to be y values. I can see that my starting point is 2 and my ending point is 10. The last thing I need is an expression for the length of each rectangle. Well, each rectangle stretches from the f curve all the way to the g curve, or the g curve is first, I guess, then the f curve. Now, since this is a horizontal distance, the horizontal length is going to be the difference in 2 x values. The shorthand we could write x sub f, like the x value of the f function minus the x value of the g function. In reality, if we had expressions, you would need to solve both of these equations to get x by itself. And then you would use this one first, and you would get an expression with y, and you would subtract this one, another expression with y. For now, I'm just going to do shorthand because you're about to do a bunch of examples. So the starting and ending are obviously your limits of integration. And then we have an x value from the f function minus an x value from the y function, which together represent the length, and there's dy. And this is your integral, and this accurately represents this shape. Okay, I'm going to stop here and give you practice problems. Find the area of each of the shaded regions on the screen. Once you have your integral correctly set up, you're welcome to use your calculator to find the final answer. If you get stuck, use the YouTube link that's at the bottom of the question to see how I worked it out. Focus on making sure that you understand the answer before you move on. Here are the next 3 practice problems. Just like before, work out the integral on your own. If you get stuck, use the YouTube link. Here are the next 3 practice problems. Continue to focus on making sure you have the setup correctly. Remember to avoid the mistakes that I warned about at the beginning of the video. These are the final 5 practice problems. For these problems, you're not given a graph, which means you'll need to create your own sketch. I recommend using Desmos. Notice that in some of these, you're just given a curve. You can assume that that's y equals in front of that curve. When there's an x equals, you can graph it like this in Desmos, or you can try to solve for y first. Good luck. Nice work. That's it for topic 1. Again, if you need help, please don't hesitate to reach out.